Okay, so today I have a really fun video. We're going to be doing calculus using SymPy. I basically have in this first section from SymPy import asterisk. If you don't want to do this, you can do import SymPy as SP, something like that, and you'll just have to use SP before everything. Then from SymPy, I'm going to import init printing, which is some nice LaTeX display, and I have the symbols we're going to generally be using. So X, Y, and Z, and we're going to define it to be that. So let's run this. Now let's move on. Here I have basically the really common differential functions in SymPy. If you're comfortable with SymPy, you can copy this and go ahead and use it yourself. But we're going to get into it, and we're going to talk about it slowly. We have x cubed. So this is basically diff, which is differentiate, x cubed, which is our function, and with respect to x. So we run this. It gives us derivative. Now we can do dot subs to substitute a value. So we want to substitute x and 2. So this should give us 12. So it's going to take x and put 2 where it is, and then it's going to square it, obviously, because it's going to stick 2 there. So we should get 12. And we do. Now let's move on. Arctan of y divided by x. So we're taking derivative, and I'm using this derivative over this one, because this will display it nicely before it takes the derivative, to make sure that you inputted something correctly, to make sure you have the right order, and so forth. So we're going to do a tan y divided by x, and we want to differentiate that with respect to y or x. I'm going to do y, and I'm going to run it. So it says partial of this function with respect to y. And then we can tell SymPy to do it. And then it will compute the derivative with respect to y. And I prefer this way to make sure that I'm taking the right derivative with respect to the right order. So if I do y comma y, and I remove this, it shows me this, right? Or if I do y comma x. So it allows you really to see clearly what you're doing before you differentiate. Now let's do derivative of x times y times z, comma x. So the second derivative with respect to z, we'll do the fourth derivative with respect to x, and the first derivative of y. And then we can tell SymPy to do it, but there's really no point because I don't really care to see what this is. Probably something pretty long. Let's see. Okay. Now we're going to do integration. So if you're comfortable, you can just take this and move right along, but we're going to be doing some fun stuff ourselves. So let me leave this here for a second. And here are basically your Cartesian, cylindrical, and spherical basic integrations. So you want to just use this. I use it all the time. It's very helpful. We're sounding it out. We're going to do exp minus x squared comma x comma minus o comma o. Oops, int. There we go. And we know that this is the square root of pi. You can also do this. Square root integral exp minus x squared plus y squared. And then we can just take this. Y, and this should give us the same thing. 2 commas again. So if we say do it, again, we'll get the square root of pi. So these are actually equivalent, and you can play around by timesing this function by e to the minus y squared, and then taking the square root. So it's pretty neat to see how to get this from. Anyways, we'll move on. We're going to do sums now. So sums are really fun. Series and computing their sums. Who doesn't enjoy doing that? So we're going to do sum, and we're going to be computing the sum of, which is what I want to do, it's minus 1 divided by 8 to the n. Now, in series, we always have n to be an integer value, 1, 2, 3. So let us now define n to equal symbol, n, and we want integer equal to. So this is telling SymPy that I want n to be an integer. I'm going to do n. I'm going to go from 0 to infinity. So if we display it, there it goes. Now if we want to compute the sum of this, say do it, and it'll be 8 over 9. So that's really neat. This is really one of the coolest things, I think. Now we're going to do Taylor expansion, and we're going to do Taylor expansion of the gamma factor. So we need v comma c equals symbols, v comma c, and we want our function, so func equals 1 divided by square root 1 minus a divided by c squared. And we'll now display func, and now we're going to do series. So this will expand the series of the function. Now we want it with respect to v, because v is a variable, c is a constant. And we want to do around 0, so it's around the very small amounts of v. And we want to do, let's say, 4 terms. Okay, so we now have the expansion of the gamma factor. Thank you guys so much for watching.